We will talk today about contaminant transport some more. Last time we made the case that the mechanisms by which transport occur are by diffusion and dispersion. Diffusion being molecular diffusion, Brownian motion, which is quite a slow process, similar to diffusion of odors, if you like, in air, but in water in this particular case. And mechanical dispersion is something that looks like that, but actually is much faster and occurs really due to mechanical mixing. So those are two methods of spreading, of increasing entropy, if you like, increasing disorder in a system, if you talked about it in a thermodynamic sense. And added on to that is the behavior due to advection. And so all of these were something that we were interested to do to be able to say, what happens if you pick up from a source dissolving components that are held in place as free phase, and from that you carry it downstream and you develop a plume which is defined by, in this particular case, this kind of stippled region, which is the effect that comes from dissolution that ends up gathering somewhere downstream. So that's kind of what we talked about last time. So what I want to do today is to enlarge on that a little bit and to be able to take the information that we had about those mechanisms and to translate, thank you, and to translate those into what their effects are in the bigger picture. So that's kind of our goal for today. And so the picture that we're looking at, I suppose, if we look at it in overview, is that you can imagine that we're looking at a source that over time emanates from a region and gets carried down gradient. And it gets carried down gradient because there's some flow velocity attached to that. And we made the case that we could represent that as something that would look like this core or a tube that would be carrying a tube that's filled with soil, of course, that would carry fluids along it due to some fluid velocity that's applied, and that we could use that to look at, if we wanted to, what the longitudinal profile would be in this x direction, downstream direction, in terms of concentration gradient. I'm not sure what colors we used. I'm going to use green. C over C0, which would range between 0 and 1. And physically, what we've looked at before is that this would look something like plug flow if there was no dispersion. And if there was dispersion, maybe you just use a different color green. And I can make this larger, of course. If there was dispersion, then physically what this would look like is something like this. Dispersion. So that was basically our idea last time. So this is, you see, this is I don't know if you can see this. This idea is that this is the distribution of contaminant as it goes downstream, kind of done in side view. But if we want to be able to understand this, then we need to understand the principal behaviors that control our system. And those principal behaviors are defined, and we said that we would never really hold you to it, but they're defined in terms of this advection-dispersion equation, which we can write out here, which is a first order in terms of time, a second order differential equation in terms of space, plus a first order term. We made the case that this is diffusion dispersion. This is advection, and this is accumulation. And it's important to note that the accumulations are not of fluids, but of mass dissolved in fluids. And that of these, this part here is part of a conservation, it's really a conservation equation with fixed law thrown in and a rule that says something about advection thrown in. And this is mass in minus mass out equals accumulation. And of course it's dissolved mass accumulation. So it's mass. So not as in the flow equations, it's fluid mass, it's mineral mass that's dissolved in the components. And so that is our expression that defines behavior. We've written it in one dimension because that's convenient for us. We'll see that it has extra dimensions to it. I guess we saw that last time also. And so we have to wonder a little bit about what these coefficients are. Well, this clearly is advective velocity is equal to Darcy velocity divided by porosity, which is equal to Darcy velocity is hydraulic conductivity over porosity head gradient, for instance. That's one of the ways we could write it. We could also write it as being equal to permeability, porosity, and viscosity times pressure gradient. They're just different ways of writing that. But the important thing is it's the rate at which the particles of fluid are moving, not the bulk of motion. So in other words, how quickly it takes to traverse across the system. And the other important feature was this dispersion coefficient, which we define as being two components. D star plus this longitudinal dispersivity multiplied by the advective velocity in the x direction, always in the down gradient direction. And we've chosen our coordinate system to be in the maximum flow direction. And so this is, you might remember that we said last time that d star we can think of as being equal to some tortuosity coefficient multiplied by the coefficient of free molecular diffusion, the thing you get out of a reference book for how quickly salt diffuses in water, for instance. That would be this. So this would be the free diffusion coefficient. Also meters squared per second, as this must be. And this is just a number between 0 and 1. 1 if it's there's no tortuosity, and much smaller than 1, maybe 100th if it's significant. And this is the longitudinal dispersivity. And it's in units of length. L stands for longitudinal because it's along the direction of flow. And it's multiplied by the value of whatever the advective velocity is in the aquifer. So the bigger the velocity, the bigger this term becomes, and it starts swamping this. And we made the case last time, even though I'm kind of running out of space here, that if you looked on a spectrum of different materials, maybe from sands and gravels to clays and shales as rocks that are have the permeability of shales, then the velocity at this end is small, and that the value of this longitudinal dispersion, which we're interested in here, would be approximately equal to d star, because if velocity is small, this term drops out. And the converse is that the velocity is larger. And if that's the case, then this molecular diffusion coefficient doesn't change. It's always, we said last time, say 10 to the minus 9 meters squared per second. And so as this number becomes large, then this term dominates and this becomes inconsequential, and then dispersion coefficient is just equal to alpha L times velocity. And always the velocity in the down gradient direction, because of course the velocity that's perpendicular to that, by definition, is 0, right? Just take the maximum velocity, the wind's blowing, then perpendicular to that, the velocity of the wind is 0, because it's orthogonal. Just something that is maybe self-evident. So that's kind of the setting the stage of what we would like to talk about. And so I guess there are a couple of things that we might ask ourselves. And so I'll frame some questions this time as to what we would ask ourselves. So you did an assignment the first week of class, Longstreet, Nevada, as a compliance point for Yucca Mountain, as it was. Maybe Yucca Mountain will be back. And we made the suggestion that this length here to the plug flow curve should be something like, well, we can calculate it. Advector velocity is equal to length over time. So length has to be equal to advector velocity times time. So if you know how long it's flowing, you know the advector velocity, you could calculate how far that is. If we had dispersion around this thing, maybe we could still take that as the 50% point. So in other words, where relative concentration C over C0 was equal to 50. So that's a convenient conceptualization that we might use. So there's, I guess, a couple of questions that we can ask, and I'll try and keep them on the same page. And I suppose one is L equals VT okay for estimating plume location? And of course, by inference, then T, if that's the case, T is equal to length traveled times the velocity it's traveling at is the time taken for arrival. So that would be true as well. So if this is true, then this would be true. So is that, if it's not, then when are the circumstances true that that's the case? 2 would be, is the mid-concentration, in other words, the relative concentration C over C0 of 0.5, in other words, this magnitude here, is this always at length equals VT? So in other words, I'm writing in terms of equations, but basically I'm saying, is this conceptual idea of plug flow always going to yield us where the front is, and is it going to be useful for us to predict from? And that's the question that we are interested in looking at. And I suppose the third one would be, is looking at 1D transport, as we've shown above, that gives us this behavior, useful for looking at behavior that we have shown on this little schematic above, and that is for looking at 2-dimensional and 3-dimensional transport of a plume. So I guess, is 1D a good predictor of 3D? So those are 3 questions that we might ask ourselves. And so we have kind of the background to do that. We know everything about, or a little bit about, the behavior that controls our system, and that's defined in this advection-dispersion equation, which we know what the individual components are. We said that this advection part is how the plug flow moves with time and where it gets to. and that the diffusion part is how relative to that plug flow the front of that front is inclined. And we drew lots of pictures. I've probably got rid of them, but basically this idea, right? That this location of the front is defined by length is equal to velocity times time, we've assumed. And that if we know where that front is, we can always calculate where, if we get increasing diffusion or dispersion around the front, exactly what that would look like. And as we get more and more dispersion, it would look more and more like this, right? Actually, that's not very well done. As we get more dispersion, we'd be moving to get these behaviors here. And so I guess the question is, how good is that assumption, and how far off are we? When can we use it? When can we not use it? And how do we go about figuring that out? And so the route to do that is to be able to take this expression and be able to solve it for some boundary conditions. That's what PDEs are for. And so that's what we'll spend time doing, at least in overview and looking at the solutions. I'm not sure we need to solve the equations, but we could imagine solving it in a variety of different ways. I think what's on this page is just exactly what we've already looked at, and so I won't retrace that. This is just exactly that same expression that we've already defined. Bless you. Bless you. Which is one-dimensional, because it only has x and time in it. If we're looking in plan view, clearly we have more than just one dimension. We have x and y in place. And it turns out we can actually write a similar kind of equation. It would have this accumulation term. It would have the dispersion term. And it would have the longitudinal advection term, which is present here. But it actually has one other term added into it. And that term is really, in a physical sense, is allowing for the fact that in addition to this plume being carried downstream, or down gradient, so it looks like this at successive times, the front of the plume, it's able to spread not only longitudinally, which would be something that would be, whoops, could look like plug flow if we did this, but would look like dispersed flow if we did this, right? And I've run out of space on the side, but you could also look at a section across this to look at what the distribution would be. And I suppose if it was plug flow, and I've boxed myself into a corner here, if it's plug flow, then it would look like the source, like Manhattan skyline. I'll draw it down here as well. If you went across the source and drew the concentration versus y, I suppose, this is x, and this is concentration here, then what it would look like with dispersion, as you know, right, you could draw this, is this. And so, two questions. One is this going to be a good estimate of where it should be, the 50% mark? Or would it be something that might look like this, or might look like this, completely away from this? And secondly, when we look at two-dimensional behaviors or three-dimensional behaviors, how do we accommodate for this lateral spreading? And the answer is in the equation that we look at the concentration gradient across the width in the y direction, and then the amount of spreading that occurs results from that. And so that's just, it's explaining exactly, if we look at the figures we looked at last time, I think we looked at these, yeah. This is basically it, right? This is the longitudinal effect of spreading. We didn't look at it in terms of differential equations, just in terms of the process, but it means that it spreads longitudinally in the x direction, and I suppose in what we've just done now, this is the y direction. It spreads laterally. So what we'll do is, first of all, we'll look at the 1D case, where we're looking at flow in a tube that's filled with sand, say, and then we'll take this to look at the case where we have three-dimensional behavior. We need to solve some differential equations. We won't do that, but we'll just make note of the fact that the basis of what we're attempting to do is work from this advection-diffusion equation. We can take our tube, we look at the flow from the upstream, which is going at some velocity in the x direction, which I guess is this here, same as the velocity that the water comes out at. It is the advection velocity. And we can imagine some different boundary conditions that we could apply. The most interesting to us, and the one that we'll use solely, even though they talk about different ones in the book, in Fetter's book, is a constant concentration. So in other words, in terms of the schematics that we drew before, if we look at concentration versus time for the upstream reservoir, then our behavior is this. Turn it on and you hold it. So this is time t0. All of a sudden the concentration goes up to a value of, we'll call this C0. And so the ratio of C over C0 ranges from 1 to 0, just as a convenient magnitude. And then we're interested in being able to figure out exactly what the distribution of concentrations are as we go along this sample, x and C over C0. And we're interested in being able to say something about what the output conditions are when it comes out at the other end. C over C0, 1. I realize I'm probably doing this as overkill, but it would be some arrival time for one of the flows, and maybe something like this for dispersion. Right? And so to do that, all we need to do is set some boundary conditions and initial conditions. So the initial conditions would be that the initial concentration within this sample is 0. There's nothing in it. At time t equals 0, we turn on the upstream behavior so that it is this. And we solve the system of equations, well, one equation for that particular condition. And the result that we get is this solution by, classic solution by Ogata and Banks, which you'll see referenced in many books. So initially, nothing, concentration 0 everywhere along the sample. Initially, at time 0, we put at the x equals 0 coordinate, the concentration equals C0, and then we hold it there for all time. That's what that says mathematically. And then we look at the concentration a long, long, long way downstream from this. We keep a 0 away out of the picture for all times as well. So this plume never actually reaches that, and that's just a way of setting those conditions. So if you solve the advection-diffusion equation for that, so if you solve this expression for that particular boundary condition, then this is the solution you get. It defines the concentration at any point as a function of the initial concentration you apply. So if it's 1 milligram per cubic meter, then that would be C0. And as a function of a number of variables. The length downstream, I guess, so in other words, this is defining the behavior at this location L. Of course, you could replace that with some value just here. And so if we use this as being x, and this as being x, and this as being x, then that would just define the concentration at some location. So it happens to be done as is L in this particular case. So, and that's the solution we get. And so if we look at exactly what that would look like, we can define it. I think I put on my desktop something. Let's see if we can find it. See something that says Gaussian something or other. I don't see it. Oh yeah, I do. Let's see how big this is. So, can you see that? You probably can't see that at all. Let me not worry about that. Actually, let me change the settings so that the background color is something different. Let's see if this happens. Well, it does do it on here. Okay. I used that on another projector the other day, and it didn't work at all. It did on my screen, but not on the projector. So, so what we're doing is we're plotting this relationship. So this is the complementary error function, so-called, is EFRC. It's just a coefficient. It's written down here as to what it is somewhere. Maybe it is. I don't know. Did I write it somewhere? I guess I didn't. Maybe it's on the previous one. It's just an integral, so it doesn't matter. It's a coefficient that's just like an exponential, an integral of an exponential function that we can calculate with some variables attached to it, an exponential with some variables attached to it, and again the error function with some variables attached to it. So I guess I need to find that screen again. Okay, I guess that's the problem of going large, is that I all of a sudden lose this. So if we look at each of these, why won't it do it now? That's curious. So this is just doing that calculation. The error function, this is x. This is some coefficient that's gone into it times time just by using some numbers. And it plots this function as a function of x, which is the distance away from the source in the x direction. And in the other direction, it does a whole bunch of slices at different times from a small number to 100,000. And so if you look at the magnitudes that come out of that, just by running it, that's exactly what this is. And I don't know if it'll fill the screen. Yeah, it does. So does it do it? Oh, it does all kinds of things, actually. I didn't really want to do that. I don't know what it's doing. Let me run it again just to make sure, so I do know what it's doing. I thought that when okay, yeah, I can stop. All right. So this is where test my dexterity. All right, I'm going to put it there. Okay. So this is where the contaminant is introduced at x equals 0. This is the x-axis which it flows down. This dimension into the page, if you like, is time. So the profile of the plume at time 0 would be this line here, right on this boundary as it goes down here. As you go further in time, you go along this axis. So this would be a fraction of a second. This would be 100,000 seconds. And you can see as I turn it around, if I do it carefully, that not surprisingly, as you go further away from here, it's very steep. It's a very steep distribution because it hasn't had very far to be able to diffuse away from that location. And as you go further in time, then the distance here from the axis to the plume increases. So what we expect. So it's like a Gaussian distribution. It starts off very steep and it just gets stretched out over time. I guess this axis stays the same, or at least this part is in the middle part, and it moves progressively further out with the heel of my elbow, or my elbow, representing kind of the base of this as it moves out. And so what we might expect, at least for the case where we have diffusion dominated in this particular case. But that's not really the case that we're so interested in. We'd like to know the case where diffusion and dispersion can occur, as it does here, but also with advection overlain on top of it. And so what we could do is we can then look at this expression that we have here, which is this, looks like a complicated equation, but it's just a length, the advective velocity, the time when we want to get the plume defined, and a coefficient that describes the dispersion in the system. And these terms actually recur. And so if we go back and look at plotting exactly what that might look like, again, I can zoom in on this so maybe you can see it better. This is exactly that expression. This is length, velocity times time, divided by this. It's the complementary error function of it. It doesn't really matter. We've prescribed some variables: advective velocity, dispersion amount, which is very small, 0.1, and time, which is half a second. So if we look at that, and if we run that, we will get something that gives us a plot which looks like this. Very big all of a sudden. And on the bottom we have location between upstream and downstream, and we see exactly what this plume looks like as we go through this. And so this is the plume at a snapshot in time. Upstream concentration is 1, C over C0 is 1, and the downstream concentration is beginning to build where it's at the end of the sample, and it's some distribution over the length of it. So I suppose what we could do is we could take the velocity and make it bigger. We could do all kinds of things, I suppose. We could make the velocity 100, and I suppose if we did that, you could guess what might happen. It's now gone so that this is equal to 1, and the plume has gone so far downstream that it's way off the end of our core and has kept on going, so that's perhaps not a very useful one to use. So we know that if we use a velocity of 1, and if we look at a time of 0.5 seconds, then a velocity of 1 would go 1 meter in 1 second. It'll go half a meter in half a second. So if we make the dispersion a very small amount, say 10 to the minus 5, then what do we expect that that plume might look like? That seems to make some sense, right? I think, hopefully. Try and get it on here. Don't want it to be, don't know why it's taken up the whole page. Is it because this is this? No, it's not that. Anyway, so you see that basically a step function. So it's upstream is 1 at the place where the plug flow has got to, which is 0.5 meters downstream. It goes to 0, and it's basically plug flow. So we see that as we change the dispersion in the system so that it's negligible, then the magnitude of the plume changes. And just running it again so we can remember what it looks like is this. And so before, when we looked at a larger dispersion, the location where we are at 50% concentration would be, I don't think I can draw it, no, it's across here. And actually it's not very far away, you probably can't see this. This is 0.6, this is 0.8, this is 1. And so if you look at the 50% concentration, actually it's not very far off being at the 0.5 mark, which would be about here. It's 0.6. So it's not quite, so our hypothesis of what we like to explain is that plug flow works. If it gets canted over, it merely does it around a fulcrum, which is at the 50% concentration. That doesn't seem to be quite true. And so maybe what we should do is look at this a little bit more. So clearly this expression that we have here is going to be a useful expression for us to be able to define behaviors. So the other thing that we could do is we could try and, since we could juggle changing the velocity of flow, changing the dispersion, changing the length of the flow domain, we could change those all independently, but we're never really guaranteed that we're going to fit inside our plot, because the second time we did it, the plume had already gone down 100 times further in our plot off to our right. So what we could do is we could look at dimensionless analysis, or dimensional analysis. You thought you'd never see that again, but we're looking at the concentration. We could take this expression and we could divide both sides through by concentration. And we could do this with the differential equation also. So we know, actually we could do it with the differential equation. We could take change in concentration with time is equal to dispersion d2c dx squared minus advective velocity times dc dx. This is wonderful. If we solve this, we get this relationship here. And so what we could do is we could look at what are the parameters that control behavior. Clearly, concentration is one of them, but we've taken that on the left-hand side. Clearly, dispersion is one of them. Clearly, length is one of them. clearly advective velocity is one of them. And clearly time is one of them. If we look at the units of those, meters squared per second, meters, meters per second, and seconds. So there are two groups. We don't have mass involved in here. Certainly mass is included here, but there's not mass included there. So we have, in terms of pi groups, we have 4 parameters minus 2 variables, and we're going to have 2 composite variables that control our behavior. And so what we could say is that the concentration, relative concentration, is going to be a function of 2 groups. And those 2 groups will be something called, we could do it by Buckingham pi, but we can also do it by inspection. We can get one which is called the Peclet number, which is, we mentioned last time, which is dispersion, which is velocity times length divided by dispersion. When advective velocity is big, then this is a big number, bigger than 1. When dispersion dominates, it's less than 1, so that's 1. And the other one is called a Courant number, which the book calls T sub r, which is an advective velocity times time divided by length. And which describes behaviors. And so if you think about it, this TR is also, we'll talk about it, is also could be referred to as a pore volume. So the point is that we could take this differential equation that we have here. I suppose we could divide both sides through by C0. What else would you want to get into the system? I suppose we could multiply both sides through by velocity times time. And if I did that, then the expressions that would come out of it would be, well, at least we could do it by velocity. No, not velocity, just time. Multiply both sides through by time. And if we do that on both sides, then we have time on this side relative to this, so we get rid of that, and we've already got this, so nothing there. We have this term here would become what? Concentration over concentration, we don't care, so we have velocity time over x, which is length, which is equal to what we've just called T sub r. And this term, we have diffusion. These two terms cross out. We have x squared on the bottom, because it's second order. And we have multiplied by time. And if we multiply both top and bottom through by velocity, then this becomes do we have time here? This is called, so velocity times length, so this is velocity times length times length. My writing's getting smaller and smaller to fit in. This is diffusion time and velocity. And so what do we have here? Velocity times, so length is equal to velocity over time. So time times length is equal to so velocity times time is equal to length. Yeah, I'm not going to do it. Well, I'm going to give up. I thought I had that one down pat, but I don't. But basically, out of this expression, you get an expression which is the Peclet number, which is this term here. And so you'd end up with a velocity times a velocity. I'm not sure how you end up getting an extra length on the top, but certainly velocity is equal to length times time. Well, certainly you can get diffusion, dispersion, and this, but yeah, I'm not going to do it. Bottom line is that you can rewrite this expression in terms of only those dimensionless characteristics. One is relative concentration on the left, and the only other two terms you see cropping up in here are Peclet number and this term that represents what I've called the Courant number after its originator, and is really, actually, you can think of it as a pore volume. So if you look at this Courant number, which is equal to an advective velocity multiplied through by time divided by length, then no, I guess it wasn't working out because of this, right? That's what's wrong. So length is equal to velocity times time. So in this, where we have velocity times time, okay, so this is a length. So it's d times L divided by V times L times L. And if we get rid of two of those lengths, then we have exactly the Peclet number. Okay, so I redeemed myself, maybe, in my own eyes, maybe not in yours. So dispersion divided by velocity is kind of a 1 over Peclet number, right? This term here. So that's what I did wrong. So yes, so what I was doing wrong was that this product of velocity times time is a length traveled. And so what this means is this is the length traveled by advection divided by the length of the sample. So in other words, when this time is equal to 1, it means that the front has gone from the upstream part where you put the concentration in, and it's arrived at the downstream, 1 meter downstream. So it's, in other words, it's filled up one complete pore volume of the core with the water that you've injected, and the front has arrived down at the front stream. And so that's useful because it allows us to be able to characterize the behavior through this little expression here in terms of defining behavior now in terms of these coefficients. So now we can define the behavior. This expression here is just this equation that was previously on the previous sheet. The one below it now is written in terms of Peclet number, Courant number, or pore volumes. You can think of this as a number being 0 when it's 0 pore volumes, no water's gone into the sample. 1 pore volume is where the front has completely swept the sample down to the downstream end. So this is the Courant number, or pore volumes. And this involves really time, and this involves the effects of dispersion. And so we could look at the case where we have a very big Peclet number, and what we're looking at are the output behaviors. So you recall that when we looked at these responses, we could look at two things. We could look at what the distribution was like along the length of the sample, or we could look at what it looked like as it came out. Concentration as a function of time, and so if you look at concentration as a function of time, which is exactly what this is, then we can come up with our solution, right? So all I'm going to do is I'm going to put in a number for the Peclet number. We're going to look at all times into the future from 0.1 to 2. So 2 is 2 times pore volumes. And so if it's a Peclet number of 100, what do you think that curve is going to look like? So not, whoops, almost. So this is a one pore volume, 0 pore volumes. If it was plug flow, then all of a sudden there'd be no concentration until all of a sudden the front arrived, and then it would go up to 1. So this is for a Peclet number of 100, a big number. If we make the number even larger, say 1,000, or 10,000, or 100,000, or a million, see if it works with a million. What do you think would happen with that front? Does it make a new one? Let's get rid of this. Nothing to plot. Doesn't like it. Too big. Value everywhere. Yeah, okay. It doesn't see it within the plotting range. So I'll get rid of another number, another 0. So 1,000. I guess we only get to go up one more. See if it plots. Does it work again for 100, which we had before? Yeah, okay. Oh, okay, so that's the limit. So I guess what we can do is make it larger, smaller rather. So this is 50% concentration, and that is roughly at about 1 pore volume. If we make the Peclet number smaller, say 1, then all of a sudden the 50% concentration is here. This is now 0.9 instead of 1. And so 50% concentration occurs at 0.45 pore volumes, not 0.5 pore volumes. If we make it 0.01 and run it again, then the value we get is given by 50%. So this is now, you probably can't see it. This is this is point. Let me not do that. Let me zoom in so you can see it. So the axes on this are now 0.98. And so if we go down to 0.5, which I think is off the chart, it's not stopped. Flashing all over the place. So this is 1, this is 0.98. Basically the idea is that, okay, so that's fine. I don't mean to give you whiplash. If I look at point, basically the idea is that it's moved very close towards the axis. So in other words, as soon as you're looking at its behavior for very small numbers of pore volumes, it's already broken through. And that kind of seems backwards, right? Because it's not being advected down, so you'd expect it to be arriving much later. But because we have this strange, somewhat dimensionless parameter, then although it's arriving much later because it's traveling only by diffusion, that it seems, yeah, so it's not a very good, yeah, I'm going to give up on this and start drawing things by hand. It's much easier. So what happens in this is exactly what's shown in Cameo on this plot here. And that is that we've said that the behavior is controlled by 2 parameters. One is the Peclet number, which is the ratio of advective to diffusive or dispersive flow. And this value is when it's equal to 0, it's diffusion dominated. When it's equal to much greater than 1, it's advection dominated. And so you'd think that when advection dominates, that's exactly when you have plug flow, that the arrival time that you'd get would look exactly like this. So at 1 pore volume, arrives at the downstream. It exactly carries the front, which is not diffused in any way, and all of a sudden the concentration goes up from 0 to 1. As a consequence of that, the magnitude of the 50% mark is also at that point. If you start making the diffusive part larger, so if you increase this part, you'd expect that the Peclet number decreases. So if instead of using something which is 100, we use something which is now equal to 1, where advection and diffusion are present in kind of the same amounts, then the result we get is this line here. And it's strange that it's moved to the left, because this kind of implies that it's occurring faster. But it's not really occurring faster, because this isn't really a time. This is a pore volume. What it is doing is it's occurring when only maybe 0.8 of a pore volume has gone through. And so if we wanted to think about a schematic of what the core might look like that allows that to happen, is that if this is length, so not really pore volumes, if this is length, then you could think about the front as being something that looks like so this is the effect of dispersion. So some little stringers have traveled much further than the pore volume magnitudes that have been pushed in, because they've gone on these circuitous flow paths. So the early arrival of this due to, sorry, I misspoke. So this is infinity that we looked at before. The one that we're looking at, which is 100, is the one that I've not drawn but is here, which is still roughly in the same location. And as you make it so that they're roughly equivalent to each other, then it appears to occur earlier. But the reason it occurs earlier is because the Peclet number, the Courant number, which is equal to the velocity times time divided by the length, it includes this velocity term, but this doesn't mean anything if the velocity is equal to 0, right? If the velocity goes to 0, then this whole term doesn't mean anything. And so the reason that it seems to arrive earlier is an aberration, because actually it's just arriving when there are fewer pore volumes that have carried it downstream. And if you use a Peclet number which is a fraction of 1, then you'd go even closer to this, which is what came up on the little GNU plot thing that we looked at. So the bottom line is that we can use these expressions to be able to say something about behavior. If you look in Fetter's book, then you'll see exactly this figure here, which is the same as the figure that I just sketched or overdrew, and that is that they look at 3 different boundary conditions for the upstream. One where you hold a concentration equal to C0 initially and for all time. One where you have a constant gradient of concentration flowing in. It doesn't really matter. The only one we're interested in is the solid one, which is this one. And you see that for a big Peclet number, it follows this form. For a Peclet number of 10, it follows this form here. And for Peclet number of 1, it follows this line here. And if it was a fraction of 1, then it would be something like this. So PE 0.1, say. Don't know. That's just a guess. But you get the idea, is that we can get the locations of these. So this is the output concentration. In the same way that we get the output concentration, we could use exactly the same expression to be able to look at the change in concentration along the sample. I suppose in this case what we do is we choose, it's not so convenient using this, but we can use it in either of these forms. So we can look at the concentration distribution along it. And that's the bottom line. So we can figure out exactly what this curve here would look like. And we can calculate that definitively. And so I guess we've answered one of our questions. One of our questions was, can we always use this point here, where one pore volume has traveled for a static front as the location of the front? Well, maybe we can if the Peclet number is equal to 100 or larger, or maybe we can get by with it's equal to 10. But if it's less than 1, then this I think is probably about 0.9 or less. And certainly as we have Peclet numbers that are smaller than that, it's not really a very good indicator at all. And so that kind of makes sense, right? Because if you think about it, the geometries that we've talked about is that in the limit, I'll go back to our very first figure today. In the limit, if we thought of a system that was diffusion only, and there's no advection in the system, then the prediction would be that this front would be 0 length along this axis for all time. And we know that by diffusion is going to carry it at some velocity, not a very fast velocity maybe, a velocity that's independent of the velocity of the water, and we know that due to diffusion it would exist along here. And so we could have probably guessed that our answer to each of these questions was whether this is a good approximation of where the mean concentration would be can't be true, because for a diffusion only case it will always predict that the mean concentration would be at 0 length along here. Hasn't traveled at all, and that's not true. And so in some cases where we have diffusion controlled transport, we have to use this expression, and we can't just theorize that the length of travel for the plug front is a good indicator of where the components would have gone. Okay. All right, we said we do two things. One-dimensional flows, well, we've pretty much done that to death. Three-dimensional flows is when you're looking now in plan view, and we have this kind of geometry that might have a plume that's developing. How do we represent that? Of course, we could overlay this one-dimensional flow, but if we do that, then we're not accommodating the fact that we can get this dispersion that occurs out to the sides, and presumably this dispersion to the sides would reduce the amount of flux that can go along the sample. And so how do we solve that problem? Well, again, there are solutions to be able to do that. In a physical sense, the solutions are quite straightforward, and it's actually directly analogous to this idea that you have a beaker that has ink in it, starts off with the ink in it at 0 time, and slowly the ink diffuses. And you could also walk across the front of the room with the beaker, and in the time it takes to get to the other side of the room, the plume will have spread. So the idea is you start off with the beaker here, you start off with the fluid, which is a skyscraper concentration, you allow it to be carried downstream for a particular amount of time, moving at some velocity of the water, and at that new time it will look different. So instead of being at this location and looking like this, at this location it will look like this instead of this. You could imagine that the areas under each of these curves should be kind of similar. And the reason for that is that the mass that was present within this skyscraper here is now present, spread out within this plume at lower concentrations, but filling up a bigger space spatially. And so this is basically the bell curve, the Gaussian distribution curve, and it's described by this. A coefficient that represents the rate at which it spreads, the time since you released it, and the advective velocity as it gets carried downstream. And if you think about it, this center of mass that's described by this is really just a length away from its upstream origin. This is equal to a length that's traveled in a given time. And so the solution really you could think of is just offset by a certain amount. This is where it started at x0, y0, and this is where the center of mass is at any particular time. And so if we record in our coordinate system where we are, it's really just subtracting the amount of velocity that's there, the distance it's traveled from the origin, and the location relative to those two places. So really, the solution is just a Gaussian distribution around this point. If you remove the idea and choose a coordinate system that instead of being this global coordinate system, which is fixed, right? X and Y fixed, this is where the house is, this is where X and Y are, the house is still here, this is where the plume's gone. If instead of choosing that fixed coordinate system, you choose a more moving coordinate system that always sits in the middle of the cloud, which is this origin here, and use uppercase X and uppercase Y to define X and Y relative to that, then the solution is much simpler. It's always a bell curve. It always has a mass of, in terms of kilograms of pollutant that's present within the system. The dispersion coefficients in X, Y, and Z directions for longitudinal and transverse dispersion. The time since it happened, these coefficients, and the location relative to this coordinate system here. So in other words, if you at time t are interested in finding out what the concentration is at this particular spot here, then its uppercase X coordinate would be this, and its uppercase Y coordinate would be this. Nothing more than that. And so what you can do with that is that you can look at what the concentration would be at the center of the plume, which is where this is equal to 0, this is equal to 0, and this is equal to 0. Exponential 0 is 1, and so the maximum concentration will be right in the center of this, and it'll be given by this amount, which is just this. And you can see that when time is a very small number, this will be large, and when time progresses, the denominator gets larger, and so the concentration gets smaller. And so if you take a cartoon of what this would look like and look at the spreading of it, it starts off here quite concentrated. Entropy increases some more, and it's really just the spreading of this curve. And so the convenience of writing it in this coordinate system, and really, I suppose, you could think of it as being something that looked like at time 0, it would look like this. At time 1, it would look like this. At time 2, maybe it looked like this. So at these individual locations, time 1, times 2, and time 3, it would look like this. So the utility of doing this is that you can describe the amount of spreading that occurs as a function of diffusion in these local coordinates. And so 3 standard deviations, because this is basically a bell curve, a Gaussian distribution. I think 3 standard deviations includes 99.7% of the mass or something like this. This length that you need to get to 3 standard deviations is given by this amount here, which is 2 times the dispersion times the time that's elapsed. And so the utility is that if you know what the dispersion is, or if you know what this is, then you can use that to calculate what 3 sigma x would be. So in other words, you could calculate exactly what the size of this plume would be downstream from this. Or alternatively, if in situ, you could somehow know by looking into the ground exactly what the plume looked like and what this length in terms of 3 standard deviations was, you could calculate what the dispersion would be. Do it either way. But either way, this conceptualization of a Gaussian distribution starts off very steep at time 0, disperses as it goes downstream and flattens out, gets less tall and much wider. The same area, if you like, under the curve, you can characterize in terms of this local coordinate system, which is just moving down, so that at any given time, its length down gradient is just given by the advective velocity multiplied by the time since it was initiated here, relative to the time that you're looking at. And so you can either calculate the size of the plume if you know what the dispersion characteristics are, or you can calculate the dispersion characteristics if you know the size of the plume and the time at which you're measuring it. And so those seem to be useful things for us to be able to use. The interesting thing which we'll find out is that this dispersion value, here d sub x maybe, for looking at dispersion in the longitudinal direction, so we've called this d sub l, and we said that in terms of processes, it's equivalent to the diffusion that's in our system plus advective mixing or mechanical mixing times velocity. This coefficient which describes behavior, which is of units of length, is actually not a material property at all. It turns out that this function is about something like 1/10 of the length of the plume. So in other words, if this is the plume, then this is the length of the plume, and it turns out that the value of alpha that comes from that is returned, that is a given value. It would be equal to L over 2. Maybe I should call that uppercase L. So alpha is equal to L over 10, which is what we've just said here. And so 100 days later, the plume's going to be bigger, so alpha L will be bigger as well. So it's not a constant feature of the aquifer at all, it's a function of its scale. And, well, actually, why don't you think about that, why that might be? It's an interesting question. We'll leave that till next time. We'll talk about it next time. So think about why that might be. Why could a parameter that describes our behavior actually be a function of something that's changing with time and exposure in the aquifer? Why does that make sense? Clearly, it should really be an independent function of the system, which allows us to therefore predict what the behavior is. And so if this value of alpha is changing all the time, then it makes it a bit difficult for us to predict the behavior of the aquifer. So how do we resolve that dilemma? So bottom line is that we can calculate our transport behaviors in the system for both these one-dimensional and two-dimensional systems. That's what we've done. We need to resort to using this advection-dispersion equation, for which there are standard solutions available to us. Those standard solutions tell us something about the behavior when we are diffusion dominated, when diffusion only is occurring, and they look fundamentally different from when advection dominates, when plug flow dominates. The kinds of expressions that we used for Longstreet really only work in this condition and are not adequate at all to represent this behavior whatsoever. And so you just need to be aware of that and need to be able to avoid doing that.